Okay, so hi everyone. So for those of you who don't know me, I'm Sam Grunblatt. I'm a postdoc in New York City at the American Museum of Natural History and the Flatiron Institute. And before that, I was a PhD student at the University of Hawaii Institute for Astronomy. And so for the past few years, I've been leading a TESS guest investigator program, as well as a complementary NASA Keck program to characterize planets transiting red giant stars that are found within the full frame image data of TESS. Oh, try that again. There we go. Okay, so just to provide some context, over the last 25 years or so, exoplanet scientists have gotten really good at finding planets transiting main sequence stars. But as we move to subgiants and red giant stars, they remain pretty poorly understood. And so, in fact, less than a decade ago, there weren't any planets that we knew at short periods around evolved stars. And so it was commonly believed that such planets couldn't actually survive post-main sequence evolution. And so the general idea was that all planets that were at separations less than about 1 AU had inspiraled into their host stars before those stars reached the giant branch of stellar evolution. But in 2019, we showed that that wasn't true through the first systematic search for planets transiting evolved stars. And so here I've just plotted planet occurrence as a function of planet radius, there we go, and period. And our survey found 3 hot Jupiters, which corresponded to an occurrence rate of around 0.5%, which was in general agreement with what's been found for main sequence stars. But if we focus solely on the planets that have periods less than 10 days, we see that for main sequence stars, planet occurrence seems to decrease with planet radius. But based on our red giant star sample, we found that planet occurrence seems to increase with radius around evolved stars. And so I'll note that this is not talking about rocky planets at all. We were not sensitive to those in our survey. But for giant stars, we should have been able to find Saturn-sized planets, but we just didn't find any. And so that led us to wonder, where did these inflated Jupiters actually come from? And so there's evidence to support the idea that these planets were formed through reinflation, that they're main sequence hot Jupiters, which became reinflated at late times around these red giant stars. And so here we're just showing planet radius versus age for K297b, which was the first reinflated planet that we found. And the colored lines on this plot correspond to different potential heating efficiencies that allow for this, the increased irradiation of the host star to get deposited inside the star and cause it to inflate. And if we compare that now to a similar mass planet around a similar mass star at a similar orbital period that is on the main sequence, you can see that the radius of K297b is significantly larger than that of the main sequence system, leading us to believe that these planets did in fact reinflate at late times. And it turns out that distinguishing between these sort of different mechanisms for causing planet inflation, proving that this could happen at these late times, really took 20 years to accomplish. But there's still a number of outstanding questions that we need to answer. For example, the dependence on the planet mass, the eccentricity of these systems, the evolutionary state post-main sequence. But now that we have TESS, we can actually do a lot better. And so, as many people in this room might already know, TESS, or the Transiting Exoplanet Survey Satellite, is surveying the entire sky to search for transiting planets around bright stars. And TESS is getting full frame images. So every 30 minutes, it's taking full frame images of the entire sky. And so that means that for all of these targets, we have 30-minute cadence data where we can start to search for new planets. And that's really great for the giant star studies, because it doesn't matter. We don't need a target list or anything. TESS is just observing the entire sky. And so we get those bright stars thanks to Malmquist bias. And so here's a plot of planet radius versus orbital period for all of the confirmed planets transiting evolved stars that we knew of before TESS. And although finding these planets was very exciting, there's a lot of questions about late stage planet evolution that we couldn't answer with just this. and to basically try and understand giant planets orbiting giant stars. All right, looks like both my mics are back on. Yeah, let me know if you can't hear anything or there are any more issues.
Yeah, okay.
Looks good. All right. Okay, so Nick Saunders is NSF graduate fellow, in case you didn't hear that before, student at the University of Hawaii, and he's been working on developing this pipeline, which we called Giants, to basically, download a whole bunch of data from TESS, where we've chosen our giant stars from a list that we've made, and then basically we take those, we use TESS cut to basically take the data for those particular stars. We then stitch together all of the sectors of data that we have from TESS, and then use a simple PCA, a principal component analysis algorithm to smooth and clean the light curves, and then perform transit analysis. And so here's just a comparison of different TESS FFI light curve pipelines for the same target. And so the simple aperture photometry is shown in black, and a light curve that's been optimized for stellar oscillations is shown in blue, and a quick look pipeline is shown in red, in yellow, and our Giants pipeline is shown in red. And so although the transit is visible in all 3 out of the 4 light curves, the scattered is reduced most significantly for the Giants light curve, as you can see here, and the transit hasn't been diluted. So that means that this pipeline is really effective at finding these low signal to noise transits, which is really important for studying giant star systems, but also might be useful for finding smaller planets. Okay, and so based on this, we were able to publish actually the target I was just showing you guys. So Nick led this publication, which is now submitted and is available on the archive. And one thing that's really interesting about this particular planet is that despite being a relatively low mass hot Jupiter that's orbiting an evolved star, it actually doesn't seem to be inflated. It's kind of at the same radius as Jupiter instead of being way up here. And although, if there are a lot of other planets that we found that are inflated, this planet doesn't seem to be one of them. And furthermore, if you look at incident flux versus radius, as we're showing on the right here, this planet is kind of down here. So it's sort of unusually small for its particular incident flux. And we think that this could be related to the evolutionary state of the system. So this is just an HR diagram of all known TESS planet hosts. And the system appears to have turned off the main sequence, but hasn't quite made it to the red giant branch. It's a subgiant star. And thus, it's possible that from a planet inflation standpoint, the system is not yet evolved enough to actually have undergone reinflation. And so this is supported by other studies that suggest that reinflation is a really quick process that turns on during RGB evolution. And so then we wanted to ask the question, okay, do other systems show evidence for inflation starting so late in the process? And so here's the next 3 planets that we found from our survey. You can see that they span a wide range of evolutionary states. One is kind of a subgiant. The other 2 are red giants at the base of the red giant branch. And unfortunately, the picture is not quite as clear as we had hoped. There isn't a clear correlation between evolutionary state and planet radius, but that's confounded by the fact that we need that all of these planets have different masses. And so we really need a larger sample of planet masses to dig into this. And so luckily, thanks to TESS and Keck, we're able to get those planet masses now. And so with now more than 5 times the planet candidates that we had previously, and most of them being pretty bright, RV follow-up is much more doable for a larger sample of these targets. And so as TESS is an all-sky survey, we've been using facilities all over the world to follow these targets up. I think we've gotten observations from 4 different continents at this point, but the majority of our observations and confirmations have come from Keck high-res. And so this is just highlighting the systems that have been characterized by Keck. So the 3 systems on the manuscript that I've been working on are shown here on the left. And you can see that 2 of these systems also have follow-up from other telescopes, improving the phase coverage and thus the orbital constraints that we had for these systems. But now on the right, here are 3 new systems that I've been observing with Keck. And among these systems, we have one is the longest period planet from our survey, which appears to be on a pretty eccentric orbit up here. The eccentricity is around 0.4, but I guess it's hidden behind me there. And we also have tentative evidence for the lowest mass planet ever found around an evolved star at around 20 Earth masses right there. And I've also been working closely with Felipe Pereira, who's a graduate student at the University of Porto, to characterize some of these planets that are transiting evolved stars in the southern hemisphere. And so although these spectrographs can't give mass estimates that are as precise as those from Keck, they seem to be sufficient to confirm these bright evolved hot Jupiter systems. Okay, so now that we've got a real population of these evolved systems, we can start to look for population-wide trends. And so this is just a plot, again, of planet mass versus radius for all planets that have periods shorter than 10 days. And I've added the planets from our survey as these black stars on this plot, where the K2 planets that we found earlier are these less opaque stars. And so you can see that there's sort of an anti-correlation between planet radius and mass that we're finding, where less massive planets are more inflated than their more massive counterparts. And showing this in a sort of log space, it appears that not only do we see this trend a little bit more clearly, but it appears that the evolved planet population has been kind of truncated. We don't see any planets that have masses larger than 2 Jupiter masses, although such planets are relatively common as hot Jupiters around main sequence stars. And so this implies that massive hot Jupiters are actually engulfed pretty quickly, which is an expected outcome for these evolved stars, and would explain why these earlier surveys didn't find any planets at short periods around evolved stars. The most massive systems weren't there, but the lower mass systems still are. And so now moving to a mass radius flux plane, we see that our evolved systems generally, although not always, appear to be kind of on the lower envelope of this planet inflation sequence. And this is implying that the planetary heating in these systems is potentially not as strong or not as efficient as it is in the main sequence hot Jupiter systems, which makes sense. Reinflation should be either less efficient than the initial planet for inflation, and also we don't have as much time to do it. The relatively short lifespan of these systems could play a role, preventing the planets from reaching a sort of steady state solution and putting on the lower envelope of planet inflation. And now to think about these systems from a sort of dynamical perspective, I'm not going to go into everything on this plot, but basically I want people to focus on these diagonal lines that correspond to a rate of orbital decay for these systems, with this upper leftmost line corresponding to a decay rate of 1 million years. And so the orbital decay timescales are getting shorter as you move toward this upper left-hand corner of this plot. And what you see is that when you add our TESS systems, this plot, they mostly lie in this sort of interesting regime or quickly evolving systems on this upper left-hand corner. And the most massive planet that we found, which is this one right here, actually may have the shortest orbital decay timescale of any known system, which is implying that even for the more massive planets, there are a lot of evolutionary effects that are resulting in things like inflation or even destruction on these shorter timescales. And so in summary, TESS has really revolutionized what we're able to do for these evolved transiting planets, and Keck is making it possible to compare these systems to main sequence systems at the population level for the first time. And so thanks to TESS, Keck, and other spectrographs, we can see that these planets are in fact inflated, although they are less so than their main sequence, than other main sequence systems, and they're also relatively low mass, again, explaining why they weren't found earlier. And so continued follow-up with TESS and Keck will constrain the dynamics of these evolved systems and can teach us more about how these planetary systems die, and potentially could even teach us about the extragalactic planet population, which I didn't have time to get into today. So that's all I got. Thanks for listening, and I'll take your questions now.
All right, any questions from the room? Evan.
All right. It's almost like I was ready for this. So one of the really cool things that we were able to do in this study is use Gaia information to locate those stars which had the craziest kinematics in our survey. And so basically, I was working with Stephanie Yoshida, who's just started her undergraduate career at Harvard College. And she's been searching for these planets around the particular sample of stars where we saw that they had extragalactic kinematics from Gaia. And unfortunately, we didn't find any planets. But we were able to put some upper limits on those planet occurrence rates, particularly in this sort of hot Jupiter regime. We find that planet occurrence doesn't seem particularly high, but that's sort of to be expected. These stars are really low metallicity, So even once you account for all the sort of metallicity effects, the age effects, things like that, you end up with, we predict that we need to search around 50,000 of these halo stars to similar precision to be able to find an extragalactic planet. With TESS, that's going to be very difficult, not necessarily impossible, but very difficult because TESS doesn't really have the precision down to those lower magnitudes. But we're going to keep trying and see what we find. I'll give you one.
Is this the right one? Okay, there's one question on. All right, we have one question from Zoom that is, do you know why less massive planets reinflate more than the massive ones?
So yes, so basically what's happening is that because the planets are less massive, basically the atmospheres are less tightly tied to the planet itself. And so it's easier to deposit the heat into those planets and then cause that inflation. When the planet is really massive, the scale height is very small for the atmosphere. And so even when you do have reinflation, the change in the radius of the planet is going to be pretty small. And so that's harder to observe.
All right, great. Well, we only have about 20 seconds left, so let's give Sam a big round of applause.